Okay, take a look at one of the most important, if not the most important equation in the chapter, and that's Coulomb's law. So F equals K, Q1, Q2 over R squared. This can be presented in a couple different ways. Your book actually presents it where it puts the value of the charges in absolute value brackets. Why so? Yeah, it can be positive or negative. You're just going to plug in the absolute value here, and you're going to have to decide if it's attractive or repulsive, depending on if they're like charges or opposite charges, and then what direction that force might actually be, because don't forget, force is a vector and has both magnitude and direction. Some books teach it that they actually put the actual values in here, and that way they just say, well, if it comes out positive, that's repulsive, and if it comes out negative, that's attractive. Because if you put in two positives or two negatives here, that would definitely come out positive. But if you put one positive and one negative, which would be attraction, then it would come out attraction. So some books teach it that way. Your book chooses to use absolute value brackets, great. So I'll go with that convention. All right, so this is your equation for plus minus or Coulombic attraction, Coulombic repulsion. It should look a little bit familiar to something you guys studied last semester. What might that be? Gravity. So if you remember gravity, force due to gravity looked like this. The general force due to gravity, you got a constant, we got a constant. You have masses, here we have charges instead, and then divided by the distance of separation squared. So this takes on the same form as gravity. So kind of something foundational here in terms of how forces work at a distance in this case, especially these two forces in this case. Cool, our constant in this case, so K, so is 8.99 times 10 to the 9th. It does have units, and I never remember what those units are, but Newton meter squared per Coulomb squared. So, and again, I struggle to remember these units, but I take it on faith that as long as I use SI units everywhere, things are going to work out. So K here does have units. So Q, what units should those have for SI? Coulombs. And then R? Meters. And as long as I use all SI units, guess what the force comes out in? Newtons. Sweet. So take it on faith if you forget these units and stuff like that. I'm a big advocate of always making sure you write your units in, but sometimes on K I get a little bit lazy, so I will try not to be lazy today. But I still highly recommend you put your units on everything you do. Cool, we'll find out a little bit later on that this K is actually related to what we call another constant, the permittivity of free space. We'll see that with Gauss's law a little bit later. All right, so let's kind of see how this works out with question number 2 on your handout. Question number 2 says 2 point charges are of 1 microcoulomb each, are 1 centimeter apart. And the question is, what is the magnitude of the force experienced by either of the point charges? So in this case, is it attraction or repulsion, first of all? Repulsion. So notice, it's hard to put a direction from the get-go on this equation because it depends on how your charges are arranged. Is one on top of the other, one in front of the other, one left, one right, you know, and so it's somewhat arbitrary in there, but what you can determine is it attraction or repulsion. So for the charge I've drawn on the right, in my drawing, what direction would its force, it feels, be? To the right. To the right. Cool, and the one on the left? To the left, but that's only because I drew it one on the left, one on the right. If I'd drawn one on the top and one on the bottom, it would still be repulsion, but I'd have to change that. So that's why it's hard to put directionality somehow built into this equation. It's going to take into account what you know, so about attraction, repulsion, and how the diagram is set up. In this case, we see 1 centimeter, and what should we immediately think? And what is it in meters? 0.01. Good. Cool. And from here, if we want the magnitude of the force either one feels, it's the same calculation. So just equal and opposite directions according to Newton's third law. So in this case, F equals 8.99 times 10 to the 9th, Newton meter squared per Coulomb squared. If I can write that. Make sure you put microcoulombs into plain old coulombs. And in this case, since Q1 and Q2 have the same charge, I'll just square it. And then divided by 0.01 meters squared. Cool. Anybody want to do this one in their head? I chose the numbers nice so that you could. So if you notice, 1 times 10 to the minus 6 squared is 1 times 10 to the minus 12. And if you multiply this by 1 times 10 to the minus 12, what do you get?
8.99 times 10 to the minus
Good, 8.9 times 10 minus 3, but then dividing by 0.01 is the same thing as multiplying by 100. So it's 1 over 100. So dividing by that squared is multiplying by 100 squared, which would be multiplying by 10 to the 4th, which is going to get us what? Joseph.
8.99.
Is it just 8.99 straight up? 10 to the... I had 10 to the minus 3, and then I had 10 to the 1st. Do I not get 10 to the 1st? Am I getting that wrong?
I thought it was 10 to the 4th.
So...
89.9.
Okay, so good, times 10 to the 1. There we go, which is the same as 89.9 newtons. Cool, because if you notice, let's go back and review this one more time in our head, but you should definitely use your calculator. 1 times 10 to the minus 6 squared is 1 times 10 to the minus 12. Dividing that by 0.01 squared would be the same thing as multiplying it by 10 to the 2 squared, or 10 to the 4th. So 1 times 10 to the minus 12 times 10 to the 4th, essentially, or divided by 10 to the minus 4, same def, would get you 1 times 10 to the minus 8. If you multiply this by 1 times 10 to the minus 8, that's where you get the 8.99 times 10 to the 1 power, or 89.9. All right, problem number 3, you're given this lovely diagram with these 3 charges, and what are you asked?
What is the net electric force experienced by the -1 microcoulomb?
Is it micro or nanocoulomb? Oh, nanocoulomb, yeah. By the -1 nanocoulomb charge. So we got this guy, and I don't know what force he experiences. Now, why is he experiencing a force, first of all?
Because there's 2 other point charges.
2 other point charges in the area. So what direction is the force he's going to feel from this point charge right here? To the right. These are like charges, so they repel, so this is going to be to the right. So, and what's going to be the direction of the force he feels from this point charge? Attractive force, so towards it. We'll have to figure out what angle that is and stuff like that in a little bit, but it shouldn't be too bad. I made the numbers kind of nice here. Cool, and then if I want the net force, well, force is a vector, so when I add these, so I'll have to break this guy into components and stuff like that, add the components and put it back together to get the vector sum here. So in this case, let's deal with this one first because it's all in the positive x direction. That's going to be easier. So in this case, that force F equals K. So, and in this case, between these two, if I put in absolute values, I'll be putting in 2 times 10 to the -9 coulombs and 1 times 10 to the -9 coulombs all over. And what distance are they separated by? And how much is that in the SI unit meter? Yeah, 1 times 10 to the -6 meters. Cool. We'll figure out what that is in a second. Our other force here, if we do something similar, F equals K, and Q1 here, 4 times 10 to the -9 coulombs. Q2, 1 times 10 to the -9 coulombs. And what's the distance of separation here between these two? Yeah, it's the hypotenuse of this right triangle. And so 1 micron squared is going to be the square root of 2 micron squared, which I'll make, actually, let's just make it square root of 2. So, but square root of 2 times 10 to the -6 meters, all squared. So essentially 1.414 times 10 to the -6 meters squared. Cool. When I go to add these, though, I'm going to have to break this into components. Let's actually get absolute values for these real quick. What is the value for the force of this guy here?
I got 17,980.
Good, I got the same thing. How about this guy right here? Did you get the exact same number? Mm-hmm. All righty. Why did it come out to be the exact same number? What's going on here? Well, sort of. That's half of it. But if you notice, how much do these numbers? So this one's identical. So how many times bigger is this number than this number? 2 times. But this number is square root of 2 times bigger than this number. But then we square it, which makes it double as big as well. So we've doubled the numerator and doubled the denominator. And lo and behold, it comes out exactly the same number. So, however, we go to add this into components here. So this guy, again, is all x. So he's 17,980 newtons and 0. So, but this force right here, what is this angle relative to the x-axis here?
45 degrees.
Yeah, if x and y are equal, that must be 45 degrees. You could technically say tangent of theta equals 1 over 1, and the inverse tangent of 1 is 45 degrees. So then what is the x component of this force right here?
45. Or F, cosine 45.
Cool. Now, if we just use 45 degrees, technically, had we started from 0 and used 135 degrees, this would work out already. But I've taken advantage. If I use the reference angle of 45, then is this in the positive x or negative x direction? Good. I better account for that if I'm using just the reference angle. Cool. And what is the y component? Good. 17,980 sine 45, and it's in the positive y direction. Great. So if I add these together here, somebody want to get me 17,980 sine of 45?
Sine of 45 or cosine?
Sine first. I'm gonna actually just put numbers in here.
12,713.77.
One more time.
12,713.78.
Cool. And how about a y component here? I'm sorry, x component here by adding these together, or technically subtracting, however you want to look at it. Okay. So in this case, if I had to redraw this guy, what direction is that in overall, that force? Relative to him, where's that net force going?
Up and to the right.
So in this case, we've got positive x a little bit, and positive y more so, and the net up and to the right. Sweet. And in this case, what is the magnitude of that force if we use our Pythagorean theorem? Cool. And what about the angle relative to the x-axis here?
degrees.
67.5 degrees. Great. Anybody want to confirm that? 67.5 degrees.
So already confirmed.
If Chris gets it, it's confirmed. Like charges do what again, Chris? Just checking. All right. So in problem number 4 here, we've got these lovely two spheres that have exactly the same charge. And if they have the same charge, Chris, what kind of force do they feel with each other? Repulsive. Sweet. So they're repelling each other until we reach equilibrium here. So if we draw a free body diagram, so the question is what's the charge on them, by the way. So we'll have to figure out how far apart they are and do Coulomb's law and solve for Q. In this case, though, setting up a free body diagram, what forces are acting on either one of these lovely spheres?
Repulsive force.
Got the repulsive force. So for the one on the right, that would point this way. And so I'll just call that, actually we'll just set it up, F equals K Q squared over R squared, since they have the same Q. Okay, what other forces? Yeah, we just got its weight, so mg. And what else?
Tension.
Good, and we got the tension in the cable here as well. Cool, so, and we can look at either one. They got the same free body diagram essentially in opposing fashions as far as the Coulombic force. But in this case, we can set up the sum of the forces for the x and the sum of the forces for the y direction. And is this lovely sphere moving? No. So it's not even moving. Is there a net acceleration that it feels in any direction? No. So then is there a net force it feels in any direction? No. So notice some of the forces always adds up to ma, but if there is no a, or if your acceleration is 0, that means it adds up to 0. And so in the x direction, what forces are operating in the x direction?
Gravity.
X direction?
Oh, I'm sorry. Repulsion.
Yep, Coulombic force here. So here we're going to have kq squared over r squared in the positive x direction, and then what's balancing that out in the negative x direction?
The tension.
So all of the tension?
Just
Cool. What is the part of the tension in the x direction?
T cosine.
Cool. And what theta are you referring to when you say t cosine theta?
No.
Good. Notice 5 degrees is the angle to the y-axis, right? So when we...
85.
Good. So you can say t cosine 85 or t sine 5. Take your pick. I like just getting the angle relative to the x-axis and saying, well, I know that's 5 degrees. That means this angle right here is 85 and using t cosine 85. But you could do it the other way. Cool. And that'll equal 0. What about the y direction? What forces are operating in the y direction?
T sine.
Good. T sine 85 degrees in the positive y and in the negative y.
Mg.
Cool. And that will equal 0 as well. Cool. What am I trying to solve for again? The charge. So in this case, to get this charge, I have to know everything else in this equation. What am I not going to be able to find directly in this equation just yet? Tension. Could I get that distance of separation? Because I don't know that yet either. How do I get this distance right here? Yeah, so in this case, how far is this distance if the string is 10 centimeters and that angle is 5 degrees? How far would this be? What? Yeah, 10 times sine of 5. So then how far would the entire distance of separation be? 2 times that. So in this case, we're going to find that r equals 2 times 10 sine 5 degrees. Can anybody get me what that r value comes out to? Glad you went and got your calculator, Joseph.
1.74 degrees.
1 point what?
74 meters.
Ah, so that's better. 74, actually 1.74 what? Centimeters, which means, what does that equal in meters?
0.0174.
Good. Cool. All right, so we know r, and we know k, it's a constant. I just don't know t. So where are we going to get t from? From our sum of the forces in the y direction. The only thing we don't know in this equation is t, so we'll solve for it. And so in this case, t is going to equal mg over sine of 85. So in this case, 0. What is our mass?
0.01 grams.
What is our mass? Not.
0.01.
Ooh, we got to put it in kilograms, though, right? So what is that in kilograms?
0.000040.
4 zeros and a 1. Great. 1 times 10 minus 5 kilograms. 9.8 meters squared for gravity, all over sine of 85 degrees. Can somebody get me attention? Somebody give me attention, please. Somebody didn't get the double entendre there. All right.
Yeah, I got it. 9.83 times 10 to the negative 5 newtons.
Good. Now we'll substitute that back into this expression to solve for Q. So in this case, if we have 0.99 times 10 to the 9th Newton meter squared per Coulomb squared times Q squared all over our R squared. And I'm just going to move this over to the other side. And so it'll be 9.837 times 10 to the negative 5 newtons times cosine of 85 degrees. Cool. So coming out after I square root it with 5.37 times 10 to the negative 10 coulombs. Anybody want to confirm that?